If you fell into a black hole, you would die twice. Not metaphorically, not in some philosophical sense. You would actually experience two completely different deaths. And here's what breaks everything we think we know about reality. Both of them would be real. From your perspective, falling in, you'd cross the event horizon. You'd pass through that invisible boundary, continue falling inward, and eventually reach the singularity at the center. From the moment you get close to the moment you die, maybe 20 minutes pass on your watch. It's over. Done. You're gone. But there's another version of this story, from your friend's perspective, watching from a spaceship at a safe distance. You never cross the event horizon at all. They see you falling, getting closer and closer to that boundary, but you slow down. You get slower and slower and slower, asymptotically approaching the edge but never quite reaching it. Your image freezes there, stuck at the boundary of the black hole, gradually fading and redshifting over timescales longer than the current age of the universe. Same event, same black hole, same moment in time, two completely fundamentally different realities. So which one is true? Did you fall through and die? Or are you frozen at the edge forever? The disturbing answer is both. You crossed the horizon and you didn't. You died quickly and you're still there. These aren't approximations or tricks of perception. Both descriptions are equally valid, equally real, equally correct accounts of what happened. This is the paradox at the heart of black holes. It's not just about extreme gravity or darkness or things getting destroyed. It's about reality itself fracturing into incompatible descriptions that are somehow both true simultaneously. It reveals something profound and unsettling about the universe we live in. There is no single objective timeline. No universal now, where we can all agree on when events occur. Reality depends on where you're standing, how you're moving, and what you can observe. And nowhere is this more extreme, more impossible to wrap your mind around than at the edge of a black hole. To understand how this paradox is possible, we need to walk through what actually happens when you fall. Not the Hollywood version, not the science fiction imagination. The real physics of it, step by step, from both perspectives, because the truth is stranger than any fiction. Let's say you decide to do this. You're going to fall into a black hole. You've done the calculations, you understand the risks, but scientific curiosity wins out. You want to know what happens at the edge of the most extreme objects in the universe. You want to experience it firsthand. First decision, which black hole? This matters more than you might think. There are two main types. Stellar mass black holes, formed when massive stars collapse, typically have masses between 5 and 100 times our Sun. Then there are supermassive black holes, the giants at the centres of galaxies, with masses millions or even billions of times the Sun's mass. You're going to choose a supermassive one, specifically Sagittarius A star, the black hole at the centre of our Milky Way galaxy. It's about 4 million times the mass of the Sun. Why does this matter? Because of something called tidal forces, the difference in gravitational pull between your feet, closer to the black hole, and your head, farther away. For a stellar mass black hole, these forces would rip you apart long before you ever reach the event horizon. We're talking about forces millions of times stronger than anything on Earth, stretching you like taffy in a process physicists actually call spaghettification. But for a supermassive black hole like Sagittarius A star, something remarkable happens. The event horizon is so far from the singularity at the centre, millions of kilometres away, that the tidal forces at the horizon itself are surprisingly gentle. Gentle enough that you could cross completely intact, alive, conscious, without even necessarily realising you'd passed the point of no return. So you point yourself toward the centre of our galaxy and let go. The fall begins. At first, nothing seems particularly unusual. You're in free fall, weightless, drifting through the darkness of space. But you're accelerating, constantly accelerating. The black hole's gravity is pulling you faster and faster. As you get closer, things start to change. The stars behind you begin to shift. Light from the rest of the universe is being bent, curved around the black hole's massive gravitational field. You see distortions, multiple images of the same stars, as light takes different paths around the warped space-time. Ahead of you, there's darkness. Not because the black hole itself is a dark object you can see, but because it's a region where no light escapes to reach your eyes. It's an absence, a void, a perfect blackness against the stars. You're getting closer to the event horizon now. From your perspective, from the readings on your instruments, from everything you can measure, you're approaching this boundary at an accelerating rate. Your watch ticks normally. Your heart beats at its regular rhythm. Subjectively, time feels exactly as it always has. You check your clock. 10 minutes until you reach the horizon. 5 minutes, 1 minute. The event horizon isn't a physical surface. There's no wall, no barrier, no membrane you can touch. It's a mathematical boundary, an invisible line in space-time defined by a simple rule. Inside this radius, escape velocity exceeds the speed of light. Nothing, not even light itself, can move fast enough to get back out. 30 seconds. You brace yourself, not sure what to expect. Will there be some dramatic transition? Some moment where you feel yourself crossing? 10 seconds. 5, 3, 2, 1, 0. You cross the event horizon and nothing happens. No flash of light, no sudden jolt, no sensation of passing through anything. You're still in freefall, still weightless, still looking at your instruments showing you're accelerating inward. The only difference is that now, according to the mathematics of general relativity, every possible path you could take leads inward. There is no trajectory, no amount of thrust, nothing you could do to turn around and leave. You are inside. From your perspective, this was straightforward. You fell toward the horizon, you reached it, you crossed it. According to your watch, maybe 20 minutes have passed since you got close. You're alive, you're conscious, you're still experiencing reality in a linear, sensible way. You continue falling inward, toward the center. The horror will come later, when tidal forces grow strong enough to matter. But for now, in these moments after crossing, you're intact. You can still think, still observe, still exist. From your frame of reference, this is what happened. This is your reality. But while you experience this smooth, continuous fall into darkness, something very different was happening to everyone watching you. Let's rewind. Same scenario, same black hole, same fall, but this time we're watching you from a spaceship hovering at a safe distance, far from the event horizon. We see you begin your descent. At first, everything looks normal. You're falling, accelerating toward the black hole, getting smaller as distance increases between us. We track you with our instruments, watching your velocity increase as gravity pulls you faster and faster. You're approaching the event horizon now, getting closer. And then something strange starts to happen. You begin to slow down, not from your perspective. You're still in freefall, still accelerating from your own point of view, but from ours, watching from outside, your motion appears to decelerate. You're moving slower and slower as you approach the boundary. Why? It's not that you've hit the brakes. It's not that you've somehow stopped falling. It's because of light. The photons bouncing off your body and traveling back to our eyes, to our cameras, have to escape the increasingly powerful gravitational field. Each photon carrying information about your position has to climb out of deeper and deeper space-time curvature, and that takes time. The closer you get to the event horizon, the longer each photon takes to reach us. They're delayed, stretched, fighting their way up the gravitational well. From our perspective, you're getting slower. Your movements become sluggish, like a video playing in slow motion. Your clock, which we can see on your wrist, appears to tick more and more slowly compared to ours. You're also changing colour. The light coming from you is being gravitationally redshifted. Photons climbing out of the intense gravity will lose energy in the process, and when light loses energy, its wavelength gets longer. It shifts toward the red end of the spectrum, then past red into infrared, then into radio waves. You're getting dimmer too. Fewer and fewer photons are making it back to us. The ones that do are increasingly spread out in time, stretched thin across seconds, then minutes, then hours. We watch you approach the event horizon, 100 meters away, 10 meters, 1 meter, 10 centimeters, but you never quite get there. From our perspective, you're asymptotically approaching the horizon. You get closer and closer, but the rate of approach keeps slowing. 1 centimeter away, 1 millimeter, 1 micrometer, but never 0. The last photons that bounce off you just before you would cross the horizon, those photons take longer and longer to escape. The photon showing you at 1 millimeter from the horizon might take hours to reach us. The one at 1 micrometer might take days. At 1 nanometer, years. And the photon that would show you exactly at the event horizon, that would take infinite time. It would need infinite energy to escape, and it simply can't. It's trapped at the boundary, forever climbing but never reaching us. So from our point of view, you never cross. You freeze there. Your image stuck at the edge of the black hole. Over the next thousands, millions, billions of years, your frozen image continues to dim and redshift. The last remnants of light carrying your image shift through radio waves into wavelengths so long they're barely distinguishable from the background radiation of space itself. You fade, slowly, incomprehensibly slowly. Your image becoming a ghost, then a whisper, then effectively nothing. But you never crossed. Not from our perspective. You're still there, in principle. Your information encoded in those infinitely delayed photons at the boundary. Frozen in time at the edge forever. 2 accounts, yours. You crossed, you fell through, you're inside. Ours, you never crossed, you're frozen at the edge, fading over cosmic timescales. Both are real, both happened, both are valid descriptions of the same event. So how can this possibly be true? How can reality itself give 2 fundamentally different answers to the simple question? Did you cross the event horizon? The answer lies in something that still feels impossible, even though we've proven it beyond any doubt. Something Einstein revealed over a century ago that changed everything we thought we understood about the universe. Time itself is not what you think it is. Here's what Einstein realized, and what experiments have confirmed again and again over the past century. Time is not universal. There is no cosmic clock ticking away the same seconds for everyone, everywhere in the universe. Time is not an absolute background against which events occur. Time itself is flexible, malleable, dependent on where you are and how you're moving. This is not philosophy. This is measured, verified, physical reality. Gravity doesn't just pull on objects, it pulls on time itself. The stronger the gravitational field you're in, the slower time flows for you relative to someone in a weaker field. Not slower in the sense that you feel sluggish, or that your watch malfunctions. Your experience of time remains perfectly normal, but when compared to someone farther from the source of gravity, your clock literally runs slower. You age more slowly. Chemical reactions occur more slowly. Everything governed by time happens at a reduced rate. We know this is true because we've measured it. Right now, there are satellites orbiting Earth for GPS navigation. These satellites are about 20,000 kilometers above the surface, in a weaker gravitational field than we experience down here on the ground. Because they're farther from Earth's mass, time runs slightly faster for them than it does for us. How much faster? About 38 microseconds per day. 38 millionths of a second. Sounds negligible, right? But GPS works by measuring the precise time it takes for signals to travel from satellites to receivers. The system needs to be accurate to within billionths of a second to pinpoint your location. If we didn't account for this time dilation, if we didn't correct for the fact that time runs differently at different distances from Earth, GPS would accumulate errors of about 10 kilometers per day. Your navigation would fail within minutes. So the system is programmed to account for relativity. The satellite's clocks are intentionally adjusted to compensate for time dilation. This isn't theoretical physics happening in some abstract realm. This is engineering, working perfectly, multiple times a day, every time you use GPS. Time genuinely runs at different rates depending on gravity. Near a black hole, this effect goes from microseconds per day to something far, far more extreme. The gravitational field near a black hole is the strongest in the universe. Space and time are warped more severely there than anywhere else, and as you approach the event horizon, time dilation becomes exponential, then infinite. Let's think about what this actually means. Imagine two identical clocks. One stays with us, far from the black hole, in weak gravity where time flows normally. The other clock goes with you as you fall toward the event horizon. At first, when you're far away, both clocks tick at nearly the same rate. Maybe your clock is running 0.1% slower than ours, barely noticeable. As you get closer, the difference grows. Your clock runs 1% slower, then 10% slower, then 50% slower. By the time you're very close to the event horizon, your clock is running at a tiny fraction of the rate of ours. For every second that passes for you, minutes pass for us, then hours, then days. At the event horizon itself, the time dilation factor becomes infinite. 1 second for you would correspond to infinite time for us. Or put another way, from our reference frame, time for you appears to stop completely at the horizon. But here's the crucial thing. This is not an optical illusion. This is not about delays in light signals or tricks of perception. Time itself is genuinely flowing at different rates in these different locations in space-time. From your frame of reference, your clock ticks normally because you're measuring time with instruments that are experiencing the same time dilation you are. Everything in your local region of space-time is synchronized to the same rate, but compared to distant observers, you really are experiencing time more slowly. There is no universal now. No moment where everyone in the universe can point and say, this is the present. The present depends on where you are and how you're moving through space-time. Different observers, in different reference frames, will disagree about what is simultaneous, what is past, and what is future. This is why both versions of your fall are true. Time itself is running at such vastly different rates in these two reference frames that the events appear fundamentally different. You crossed the horizon because from your time frame, with your clock, with your measurements, you reached it and passed through. You never crossed because from our time frame, with our clock, with our measurements, you're taking infinite time to reach it. Both statements are correct. Both are complete descriptions within their own frames of reference. Let's walk through the mechanics of exactly how this works, step by step, moment by moment. Let's make this concrete with an analogy. Imagine you're sending video updates to your friend as you fall. Every second, your spacesuit broadcasts a single frame, a snapshot of where you are and what your clock reads. From your perspective, you're transmitting these frames at a perfectly steady rate, 1 per second. Frame, 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 frame. But each of these frames is a packet of light, photons carrying information, and each packet has to climb out of the gravitational well to reach your friend watching from far away. The first frames, when you're still far from the black hole, arrive with minimal delay, maybe a few extra milliseconds compared to if you were sending them through flat, ungravity space-time. Your friend receives them nearly in real time. As you fall closer, the delay grows. A frame sent from 10,000 kilometers above the event horizon takes noticeably longer to arrive. The photons have to work harder, spend more energy, climbing out of the deeper gravity. Well, maybe this frame arrives a second late. A frame from 1,000 kilometers out arrives several seconds late. The photons are climbing out of increasingly warped space-time. A frame from 100 kilometers out takes minutes to arrive. 10 kilometers, hours, 1 kilometer, days. You're still broadcasting steadily, 1 frame per second from your perspective. But the frames are taking exponentially longer to escape and reach your friend. Now you're at 100 meters from the event horizon. The frame you broadcast from this position might take weeks to arrive. The photons carrying this image are struggling against gravity so intense that they're barely making progress outward, 10 meters out. This frame takes months, 1 meter, years, 10 centimeters, decades. You see the pattern. The closer you get to the event horizon, the more time it takes for information about your position to reach distant observers. And this isn't linear, it's exponential, approaching infinity. The frame showing you at 1 millimeter from the horizon might take thousands of years to arrive. 1 micrometer, millions of years. 1 nanometer, billions of years. And the frame showing you exactly at the event horizon, that frame would need infinite time to escape. It would require infinite energy for the photons to climb out of the gravitational well at that exact boundary. So that frame never arrives. It's trapped there, forever trying to escape but never quite making it. From your friend's perspective, they receive your frames showing you getting closer and closer, but the frames arrive increasingly spaced out in time. They get your 1 meter frame, eventually they get your 1 centimeter frame, eventually your 1 millimeter frame. But they never get the frame of you at the horizon, and they certainly never get any frames from inside, because once you cross, all light paths point inward. Nothing can move outward once inside the event horizon. This is the nature of the boundary. It's not a physical barrier, it's a one-way surface in space-time itself. Think of it this way. In normal space, at any given moment, you can send light in any direction, forward, backward, left, right, up, down. Photons can travel any path through space, but space-time near a black hole is so warped that the geometry itself constrains which paths are possible. The event horizon is the surface where space-time warps so severely that all future light paths, every possible trajectory points inward. Physicists describe this using something called light cones. At any point in space-time, there's a cone of possible futures, directions you or light could travel into. Far from a black hole, this cone is symmetric. You can go anywhere. Near the black hole, the cones start tilting inward. As you approach the horizon, they tilt more and more. At the horizon itself, the light cones tip over completely. All possible futures point toward the singularity. This is why nothing can escape. It's not about speed or thrust or energy. It's that the geometry of space-time itself doesn't permit outward paths. Asking why light can't escape a black hole is like asking why you can't travel into yesterday. The structure of space-time doesn't allow it. So from the external universe's perspective, you're frozen at the boundary. The last information that can ever reach them shows you approaching asymptotically, getting infinitely close, but never crossing. From your perspective, you crossed. You experienced it. The frames exist in your reference frame. You're inside, falling toward the center. This is what physicists call black hole complementarity. Two complete, self-consistent descriptions of the same event that appear contradictory, but are both correct within their own frameworks. There's no universal vantage point from which we can say, here's what really happened. Reality itself depends on the observer, on which reference frame you're using to measure time and position. Asking did I really cross or not assumes there's an objective reality independent of observation. But general relativity tells us that's not how the universe works. Space-time is relative. What happens and when it happens depends on where you are and how you're moving. Both descriptions are true, both are complete, both are valid. The universe permits this dual reality because time itself is not absolute, but your journey doesn't end at the event horizon. For you, the version of you who crossed, what happens next is even stranger and far more violent. You've crossed. You're inside now. From your perspective, this is a real place, a region of space-time you're occupying, experiencing, observing. You're still alive, still conscious, still able to think and perceive, but you're in a profoundly strange place. Remember those light cones, those boundaries of possible futures. Inside the event horizon, they're all tilted inward. Every path you could possibly take, every direction you could move, every trajectory light could follow. All of them point toward the center, toward the singularity. In a very real sense, space itself is falling inward here. You're not just falling through space. Space is falling with you, carrying you inevitably toward the singularity at the center. There is no escape. Not because you're not trying hard enough or because you don't have a powerful enough rocket. The geometry of space-time itself prohibits outward motion. Moving away from the singularity would be like trying to move backward in time. The structure of reality doesn't permit it. The singularity isn't just in your future spatially, it's in your future temporally. It's going to happen to you the way tomorrow is going to happen. It's inevitable, unavoidable, written into the fabric of space-time itself. But you have time before you reach it. For a supermassive black hole like Sagittarius A star, quite a bit of time actually. Potentially several hours from when you cross to when tidal forces become lethal. What do you experience during those hours? You look around. Behind you, back toward the event horizon you just crossed, there's nothing particularly visible. No glowing surface, no wall, just darkness. But when you look up, away from the direction you're falling, toward the universe you've left behind, something extraordinary happens. Light from the external universe is still reaching you. Photons from stars, galaxies, the cosmic microwave background, all of it can still fall inward across the event horizon. You can still receive information from outside, even though you can never send information back. But that light is blue shifted. Remember how light climbing out of the gravity well loses energy and redshifts? The reverse happens to light falling in. It gains energy. It blue shifts. And near a black hole, this effect is extreme. The light-carrying images of the outside universe is compressed, time accelerated from your perspective. You might, in principle, see time outside moving faster, much faster. Imagine watching the universe in fast forward. Stars that would normally take millions of years to evolve from birth to death might appear to do so in minutes. Galaxies that would take billions of years to collide and merge might play out their cosmic dance before your eyes in hours. The cosmic microwave background, that ancient light from the Big Bang that pervades all of space, is blue shifted from microwaves into visible light, then ultraviolet, then X-rays. It gets hotter and hotter. From your perspective, the universe is afterglow becoming a searing radiation. This is speculative, of course. We don't have reports from inside black holes. The mathematics suggests this could happen, but the details depend on factors we're not entirely certain about. The experience might be more chaotic, more distorted than a simple fast-forward. But the principle stands. You could, theoretically, witness vast stretches of cosmic time compressed into your final hours. The future of the universe unfolding above you as you fall toward your end. During this time, you're causally disconnected from that external universe. You can observe it, but you can't interact with it. You can't send signals, you can't affect events. You can't even in principle let anyone know what you're experiencing. The event horizon isn't just a boundary in space, it's a boundary in causality itself. It divides the universe into two regions that can never communicate. Information flows one way only, inward. This has profound implications we'll explore later. Questions about what happens to information, about whether anything is truly lost when it falls into a black hole. But for now, for you in these final hours, the implications are more immediate. You're alive, you're experiencing, you're observing a cosmos time compressed and blue shifted around you, but you're falling deeper. The tidal forces that were gentle at the horizon are growing stronger. The difference in gravitational pull between different parts of your body is increasing. And eventually, inevitably, those forces will stop being gentle. Eventually, the gentle fall becomes anything but gentle. Tidal forces. We mentioned them earlier, but now they matter. Really matter. Here's what tidal forces are. Gravity gets stronger the closer you are to a massive object. That's basic. But it means different parts of your body experience different gravitational pulls. Your feet closer to the black hole's center are being pulled harder than your head, farther away. This difference creates a stretching force along the length of your body. At the same time, gravity is pulling you toward a single point, which creates a compressing force from the sides. stretched lengthwise, compressed sideways. Far from the black hole, this difference is negligible. The pull on your feet versus your head differs by an imperceptible amount. But as you fall deeper inside the event horizon, as you get closer to where all that mass is concentrated, the difference grows and grows and grows. For a stellar mass black hole, one may be 10 times the sun's mass. These forces would tear you apart long before you ever reach the event horizon. The difference in gravitational pull across just 2 meters of your height would be enough to rip you to pieces. Your feet would be pulled with millions of times more force than your head. But you chose a supermassive black hole, remember? Sagittarius A star. 4 million solar masses. The event horizon is millions of kilometers from the center, so the tidal forces at that boundary were gentle enough to cross intact. Inside, though, you're getting closer to the center, to the singularity where all that mass is concentrated, and the tidal forces are intensifying. At first, it might feel like being on a medieval rack, an uncomfortable stretching sensation, your spine elongating, your limbs pulled taut. Painful, but survivable. Then it gets worse. The stretching forces exceed what your body can withstand. Your bones, the strongest structures in your body, begin to separate. Vertebrae pull apart. Limbs dislocate. Your tissues stretch beyond their breaking point. You're being pulled into a long, thin strand. Like taffy, like pasta. Physicists call this spaghettification. That's the actual technical term. Not a metaphor, not a joke. When they write papers about tidal forces near black holes, they use this word. Spaghettification. The forces continue to grow. Your body, already stretched, continues elongating. Your molecules are pulled apart. The chemical bonds holding your cells together snap. You're no longer a coherent structure. You're a stream of molecules falling inward. But it doesn't stop there. The tidal forces grow stronger still. Your molecules break apart into individual atoms. Oxygen, carbon, hydrogen, nitrogen, all the elements that made you, now separated, stretched into a thin line of atoms spiraling toward the center. Deeper still. The forces reach atomic scales. Electrons are stripped away. Your atoms are ionized, broken down into nuclei and free electrons. Then the nuclei themselves are torn apart. Protons and neutrons separate. The fundamental particles that make up matter are scattered, stretched, falling. You're no longer you in any meaningful sense. You're not even matter as we normally understand it. You're a stream of fundamental particles, quarks and leptons, stretched into an infinitesimally thin line, falling toward the singularity, and then you reach it. The singularity, the point where all the black hole's mass is concentrated. The place where the curvature of space-time becomes infinite. What happens there? Honestly, we don't know. Our physics breaks down completely at the singularity. General relativity, the theory that describes gravity and predicts black holes, gives us an answer. Infinite density, infinite curvature, infinite tidal forces. But infinity in physics usually means our equations are failing. We need a better theory. We need quantum gravity, a theory that unifies general relativity with quantum mechanics, and we don't have that yet. Here's what we do know. Inside the event horizon, space and time swap roles in a mathematical sense. Outside, you can move freely in space, but you're dragged inevitably forward in time. You can go left or right, forward or back, but you can't stop time or move into the past. Inside the horizon, those roles reverse. You can, in principle, move freely in the time direction, but you're dragged inevitably inward in space. The singularity is in your future the way tomorrow is in your future. It's not a place you're moving toward spatially. It's a moment you're moving toward temporally. You can't avoid it any more than you can avoid tomorrow. What happens when you reach that moment? When you arrive at that point of infinite curvature? Does space-time itself break apart? Do the fundamental laws of physics cease to apply? Does something else happen? Something we can't predict with our current understanding? We don't know. And we can't know because no information can ever escape from inside the event horizon to tell us. Whatever happens at the singularity stays at the singularity. But this raises a question, a deep, troubling question that has occupied some of the greatest physicists of the last 50 years. Your information, patterns, states, quantum numbers, everything about you, your memories, your thoughts, the precise arrangement of every particle that made you up. That's information. And quantum mechanics says information cannot be destroyed. So when you fell into the black hole and reached the singularity, what happened to all that information? In physics, information isn't what you read in a book or see on a screen. It's more fundamental than that. Information, in the physics sense, is the complete specification of a system. Every particle's position, momentum, spin, quantum state. Every field value at every point in space. The exact configuration of everything. In classical physics, if you knew the position and velocity of every particle in the universe at one moment, you could in principle calculate what happened before and what will happen after. The universe evolves deterministically. Information about the past is encoded in the present. Information about the future is predictable from the present. Quantum mechanics complicates this with uncertainty and probability, but it preserves something crucial. Information is conserved. The quantum state of a closed system evolves in a way that preserves information. You can't destroy it. You can scramble it, spread it out, make it practically impossible to reconstruct, but fundamentally it's still there. This is called unitarity. Time evolution in quantum mechanics is unitary, which is a mathematical way of saying information is preserved. This isn't just abstract theory, it's built into the foundation of quantum mechanics. If information could be destroyed, the entire mathematical framework would collapse. Probabilities wouldn't add up to 1. The theory would be internally inconsistent. So here's the problem. You fell into a black hole. You were a configuration of particles, a quantum state, a specific arrangement of information. Your memories, encoded in neural patterns. Your body, made of atoms in particular arrangements. All of that is information. You crossed the event horizon. You were spaghettified. You reached the singularity. What happened to all that information? If it's destroyed at the singularity, quantum mechanics is violated. Information would be truly lost, erased from the universe. That shouldn't be possible. But if it's not destroyed, where is it? It can't escape back out through the event horizon. So it must be somewhere, encoded somehow. But where and how? This is the black hole information paradox. Stephen Hawking spent decades wrestling with this problem, and he made it worse before he made it better. In the 1970s, Hawking discovered something remarkable about black holes. They're not completely black. Quantum effects near the event horizon cause black holes to emit radiation. Hawking radiation. It's a slow process, incredibly slow for large black holes, but it happens. A black hole isn't a perfect absorber. It's gradually evaporating, losing mass, radiating energy into space. This was revolutionary, but it made the information problem more acute. Here's why. If a black hole eventually evaporates completely, radiating all its mass away as Hawking radiation over unimaginably long timescales, what happens to the information that fell in? Hawking's original calculation suggested the radiation was completely thermal, random. It carried no information about what fell into the black hole. Whether you threw in an encyclopedia or an equivalent mass of random rocks, the radiation coming out would be identical, just heat. If that's true, and if the black hole eventually evaporates completely, then the information is genuinely lost, gone forever. Quantum mechanics violated. Hawking initially accepted this conclusion. He argued that black holes really do destroy information, that quantum mechanics needs to be modified in the presence of gravity. But most physicists found this deeply unsettling. Quantum mechanics is one of our most successful theories. Modifying it to allow information destruction would undermine vast amounts of physics. The debate raged for decades. How can information escape from inside a black hole when nothing can escape? Where could it possibly go? The answer, physicists now believe, involves the event horizon itself. The holographic principle. Here's the idea. All the information about what falls into a black hole might be encoded on the event horizon, not inside the black hole but on its surface. The two-dimensional boundary contains all the information about the three-dimensional interior. Think of it like a hologram. A flat two-dimensional holographic plate can encode a complete three-dimensional image. Every point on the surface contains information about the whole structure. The event horizon might work the same way. When you fall through, the information about you, all of it, gets encoded on the horizon itself. It's smeared across the surface in a highly scrambled form, but it's there. As the black hole evaporates through Hawking radiation, that information is gradually released back into the universe. Incredibly scrambled, practically impossible to reconstruct, but not lost. The radiation isn't purely thermal, it's subtly correlated with what fell in, carrying the information back out in encoded form. This preserves quantum mechanics. Information isn't destroyed, it's transformed, scrambled almost beyond recognition, but conserved. Hawking eventually conceded this point in 2004. He accepted that information is probably preserved, though the exact mechanism remains an active area of research. But the holographic principle has implications far beyond black holes. If the information content of a region of space can be encoded on its boundary, on a surface, rather than throughout the volume, maybe that's true generally. Maybe our three-dimensional reality is itself a kind of hologram, with all the information encoded on some distant two-dimensional boundary. This sounds like science fiction. But serious physicists take it seriously. Some versions of string theory suggest the universe really might work this way. Black holes aren't just telling us about extreme gravity, they're revealing something fundamental about the nature of information, about the structure of space-time itself, about how reality is encoded at the deepest level. The information paradox isn't fully solved. We don't have a complete theory of quantum gravity that describes exactly what happens at the horizon, exactly how information is preserved, exactly how it's released through Hawking radiation. But we know this. Black holes are testing the limits of our understanding. They're places where general relativity and quantum mechanics meet, clash, and force us to think harder about what reality is. Black holes are laboratories, natural experiments in extreme physics operating at scales we could never reproduce artificially. They're not just dark objects that swallow things. They're places where the fundamental theories that describe our universe are pushed to their absolute limits, and in many cases, past their limits, to the point where they break down entirely. General relativity works beautifully for describing gravity at every scale we've tested. Planets orbiting stars, light bending around galaxies, the expansion of the universe itself. The mathematics predicts, observations confirm, again and again. But at the singularity inside a black hole, general relativity gives us infinities, infinite density, infinite curvature. An infinity in physics is usually a sign that something has gone wrong with the theory, that we're applying it beyond its domain of validity. Quantum mechanics works beautifully for describing the behavior of particles, fields, atoms, molecules. Every prediction tested, every experiment confirms the theory. It's one of the most successful scientific theories ever developed. But quantum mechanics was built for flat space-time, for situations where gravity is negligible. Near a black hole, where space-time is curved to its most extreme, we don't have a complete quantum theory of gravity. Black holes are where these two great theories of 20th century physics meet, and they disagree. They give incompatible descriptions. The information paradox is just one manifestation of this deeper problem. We need a theory that unifies them, quantum gravity. A framework that describes what happens when quantum effects and gravitational effects are both strong, both important, both shaping reality simultaneously. String theory is one attempt, loop quantum gravity is another. There are others, but we don't have a complete, tested, verified theory yet. We don't know which approach is correct, or if the answer is something we haven't thought of, yet. Black holes are telling us where that theory needs to work, what it needs to explain. They're pointing us toward the next revolution in physics. But beyond the technical questions, beyond the search for quantum gravity, black holes reveal something profound about the nature of reality itself. The event horizon is a boundary in causality, not just a region of space you can't escape from. It's a surface that divides space-time into regions that can never communicate, that can never influence each other. Once you cross that boundary, you're fundamentally, irrevocably separated from the external universe. Your future light cone, the set of all events you could possibly affect, lies entirely inside the horizon. Nothing you do can ever influence anything outside. The external universe continues without you. Time passes, stars evolve, galaxies move. But none of that is in your future anymore. You're in a separate branch of causality, falling toward the singularity in your inevitable future. And every black hole in the universe has this property. There are probably 100 million stellar mass black holes in our galaxy alone, the remnants of massive stars that exhausted their fuel and collapsed. Each one is a boundary, a point of no return, a region causally disconnected from our observable universe. At the center of most galaxies, including ours, there's a supermassive black hole, Sagittarius A star in the Milky Way. Messier 87's black hole, the first one we ever imaged directly, 6.5 billion times the Sun's mass. These giants contain as much mass as millions or billions of stars, all compressed into regions just a few light hours or light days across. Each one carries the dual reality paradox we've been exploring. For anything that falls in, there are two equally valid descriptions: the infalling observer's experience, the external observer's perception, both true, both real, both complete within their frameworks. This tells us that the universe doesn't have one master timeline, one objective sequence of events that everyone agrees on. Reality is not a single universal thing that exists independently of observation. Instead, reality is a collection of perspectives, observer-dependent descriptions, each valid, each consistent, each complete for that observer. The universe presents different faces to different viewers, and all of those faces are real. This is strange, profoundly strange. Our intuition, built from everyday experience where speeds are slow and gravity is weak, tells us there should be one objective reality, one truth about what happens and when it happens. But black holes show us that intuition is wrong. Space and time are not the fixed stage on which events occur. They're part of the show. They're flexible, relative, dependent on motion and gravity. What is simultaneous for one observer is not simultaneous for another. What is past for one is present for another. What crosses the horizon for one never crosses for another. And yet the universe remains consistent. The mathematics works. Predictions match observations. Different observers will never compare notes and find contradictions, because the ones inside the horizon can never communicate with the ones outside. This requires humility, an acceptance that our familiar notions of reality might be parochial, limited, applicable only in the gentle circumstances where we evolved. We're also learning more about black holes all the time. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole. Actually, an image of the glowing material around it, the accretion disk of superheated gas spiraling inward. But the dark shadow in the center, that's the event horizon. Or rather, the photon sphere around it where light orbits before either escaping or falling in. That image was of M87's black hole, 55 million light-years away. In 2022, they released an image of our own, Sagittarius A star, seeing the shadow of the black hole at the heart of our galaxy. These aren't just pretty pictures, they're tests of general relativity and the strongest gravitational fields we can observe. So far, the predictions match. The shadow has the size and shape relativity predicts for a black hole of that mass. But there's still so much we don't understand. What really happens at the singularity? How exactly is information preserved? Does the holographic principle apply universally? What does a complete theory of quantum gravity look like? Are there other kinds of black holes we haven't predicted? Could black holes connect to other regions of space-time, other universes even? These questions remain open. The mysteries remain unsolved. Black holes are not just the darkest objects in the cosmos, they're the deepest puzzles, the places where our knowledge ends and the unknown begins, the boundaries of human understanding, and that in itself is worth contemplating. So if you fell into a black hole, would you die twice? In a sense, yes. You would experience crossing the event horizon. You would fall through that invisible boundary, continue inward, feel the tidal forces intensify, and eventually reach the singularity. From your perspective, from your measurements, from your experience of time, this would happen. It would be real. You would die inside the black hole. Meanwhile, to everyone watching from outside, you would never cross at all. They would see you slow down, freeze at the boundary, your image gradually fading and redshifting over timescales longer than the current age of the universe. From their perspective, from their measurements, from their experience of time, you're still there, a ghost at the edge, frozen forever. Both deaths are real. Both actually happen. Both are complete, valid descriptions of the same event, because reality itself depends on where you stand, on which frame of reference you're measuring from, on which side of the event horizon you're observing from. Time doesn't flow uniformly across the universe. Gravity shapes it, bends it, stretches it. Near a black hole, time dilation becomes so extreme that it fractures reality into incompatible descriptions that are somehow both true. The event horizon isn't just a boundary in space. It's a boundary in space-time, in causality, in what can be known and what can influence what. It divides the universe into regions that can never communicate, never compare notes, never resolve which version of events is the real one. And there is no real one, not in any absolute sense. Reality is relative. This is what black holes teach us. Not just that gravity is strong, or that space is curved, but that our fundamental notions about the nature of existence need revision. The universe is stranger, more subtle, more dependent on perspective than our everyday intuition suggests. The information paradox remains partially unsolved. We still don't have a complete theory of quantum gravity. We don't know exactly what happens at the singularity. The deepest questions are still open. But that's part of what makes black holes so fascinating. They're not just objects to study, they're puzzles to solve, mysteries pointing toward deeper truths about the cosmos. Every black hole in the universe carries this paradox. The stellar mass ones scattered throughout galaxies, these supermassive giants at galactic centers. Each one is a place where space-time is warped so severely that our usual rules stop applying, where reality fractures into multiple valid descriptions. They're the darkest objects in the cosmos, yes. But they're also the most revealing. They show us the limits of our current understanding. They point toward what we still need to learn. They remind us that the universe is under no obligation to make sense to us, but that it does make sense in ways we're still discovering. In a cosmos with black holes, even death can be relative. Even the question of whether an event happened can have multiple true answers. Even reality itself is not what it seems. That's humbling, but it's also exhilarating. We live in a universe mysterious enough to surprise us, complex enough to reward investigation, elegant enough that the mathematics describing warped space-time can predict what telescopes see when they image black holes 55 million light-years away. The universe is stranger than we imagine. It's stranger than we can imagine. And black holes are proof. If this changed how you think about black holes, or about reality itself, subscribe to Nightspace for more mysteries of the cosmos. We explore paradoxes like this, places where our intuitions fail, and the universe reveals its deeper nature. And let me know in the comments, if you could ask a black hole one question, what would it be? Thanks for watching, and remember, in the end, even something as final as death depends on your point of view.